This video is on Le Chatelier's principle. So I aim for this video to be able to define a dynamic equilibrium, explain the effect of changing the temperature of an equilibrium, explain the effect of changing the pressure of an equilibrium, explain the effect of changing the concentration of reactants or products on an equilibrium, and explain the effect of a catalyst on an equilibrium. So before we can do that, we really need to know what a dynamic equilibrium is. To do that, I just want you to picture the following situation. So, say we have a puddle on a path, and it's a sunny day. If that puddle was left uncovered, then what would happen is that puddle would evaporate. But if I was to cover it up, then what would happen is that the puddle would evaporate, hit the sides of whatever I covered it up with, and then would condense back down again. And eventually, the rate of condensation would equal the rate of evaporation. And when that happens, that puddle would not change in size. The same sort of principle can be applied to a reaction. So if you have a reaction, for example, we'll use the Haber process, which is reversible. We use this symbol to show a reversible reaction. Then what will happen is initially the reaction will be quicker in the forward way than the backward way. So the rate of the forward reaction will increase, will be very fast compared to the backward reaction, but the backward reaction will increase until both the reaction rates are the same. And when both the reaction rates are the same, the concentrations of the reactants and the products will not change, and that's when we have a dynamic equilibrium. What we must have for that to happen is a closed system, and what that means is that no reactants get in and no reactants get out, or products for that matter. So you have to have a closed system, and at a dynamic equilibrium, the rate of forward reaction equals the rate of the backward reaction. And the concentrations of reactants and products do not change. And it's important that you can make that that can distinguish between those two things. Another property of a dynamic equilibrium is that it will follow Le Chatelier's principle. And Le Chatelier's principle is that any reaction at equilibrium will shift in the direction that opposes any change made to it. Now that definition you need to know. Sorry, any change made to it. And these changes can either be a temperature change, could be a pressure change, or it could be a change in concentration of either the reactants or the products. A catalyst doesn't affect an equilibrium, and you'll see why that is a bit later. So if we stick with our Haber process, so N2 plus H2 going to make NH3, and we'll just balance it, three of those. The first thing we're going to discuss is what happens when we change the temperature. Now, the Haber process is exothermic in the forward direction, but it's endothermic in the backwards direction. Now, if we increase the temperature, that is going to be opposed by the reaction, and the reaction will want to cool back down again, and the side that will cool back down again is the endothermic side. So if we increase the temperature, the reaction will shift in the endothermic direction. But if we decrease the temperature, the reaction will want to heat back up again. Think of it as going outside when it is cold. You're going to want to put a coat on in order to keep warm. So that's exactly what the reaction does. If we cool it down, it will try and keep warm by creating more heat itself. and by going in the exothermic direction. So if we decrease temperature, it will shift in the exothermic direction in order to create more heat again and oppose that change, oppose that decrease in temperature. So temperature effect is quite straightforward. If we increase the temperature, it will shift to the side, it will make it cooler again, which is the endothermic side, absorbing the heat. And if we decrease the temperature, it will shift in the exothermic direction to warm back up again, creating heat. Another thing we can change, another condition we can change for an equilibrium is the pressure. And if we again stick with the Haber process, we can see what the effective pressure will have. Now, increasing pressure basically means squeezing the reaction. And if we squeeze the reaction, we give it less space. So if the reaction can shift to a side which will take up less space, it will do that. Now, all three of these are gases in the Haber process. And gases are compressible. So if we squeeze a reaction, it will shift to the side where there's less gas, in this case less moles of gas. So if we look at the Haber process, on this side we have 4 moles of gas, and on this side we have 2 moles of gas, which is adding up the number of moles in the equation. So we've got 1 mole of nitrogen and 3 moles of hydrogen on this side to add up to 4, and 2 moles of ammonia on this side to add up to 2. And if we increase the pressure, the reaction will shift to the side with less moles. And in this case, it's the right-hand side. I have 2 moles on the right and 4 moles on the left. If we decrease the pressure, that means we're giving the reaction more space. And so it will shift to the side with more moles of gas. Now it's important that it's moles of gas in the equation rather than just moles. Sometimes reactions create solids, liquids and gases, and you have to base the effect of pressure on just the moles of gas in the reaction. The final thing you can change in order to shift an equilibrium to the left or right is the concentration of the reactants to the products. And basically an equilibrium again will oppose the change, and so if you increase the concentration of either the reactants or the products, then it will shift to the side which will get rid of that added reactant or product. Now, if you're writing an answer to a question, you can't say to get rid of it, you have to say it will shift in order to decrease the concentration of whatever you've increased again, but basically it's trying to use it up. So it'll shift to the opposite side. Of the added reactant or product. If you were to decrease the concentration, then the equilibrium will shift in order to make more again. Because if you decrease it, it's going to oppose it and therefore want to make more. So it's going to shift this time to the same side. As the added reactant or product. The final thing you could do to a reaction is add a catalyst, but a catalyst does not affect the position of the equilibrium. All it does is speed up the reaction. And so if again we take this the Haber process as an example, we add iron to the Haber process in order to speed it up. But not only does it speed up the forward reaction, it also speeds up the backward reaction by the same amount. So it increases rate of forward and backward reaction by same amount, and therefore does not shift the reaction in either direction. What it does do is it increases the rate of attainment of the equilibrium. So what will happen is the equilibrium will reach equilibrium quicker if a catalyst is there. And so this is good for the economy of the reaction, in that you don't have to keep the reaction going for as long in order to create the yield that you're going to create using the conditions you're using. So now let's look at a couple of exam questions on this. So this first one is another way they can ask you to define a dynamic equilibrium. They can ask you to give two features of a reaction at equilibrium. And those two features are to do with the rate and to do with the concentrations, reactants and products. The first feature is the rate of forward reaction equals the rate of the backward reaction. And the consequence of this is feature 2, that the concentrations of reactants and products do not change. So as I said, this can either be asked as a define a dynamic equilibrium question, which would be worth 2 marks, one for those each 2 points, or to give two features of a reaction equilibrium. What's more important though is that you can answer questions where they ask you how changing the conditions affects the equilibrium, and it's a very structured approach you need to take to answering these questions. The first one I'm going to deal with is temperature. So here it says the following equilibrium is established between colourless dinitrogen tetroxide gas, N2O4, and dark brown nitrogen dioxide gas, that's NO2. It says use Le Chatelier's principle to explain why the mixture of gases becomes darker in colour when the mixture is heated at constant pressure. So we're heating up this mixture, and if it's getting darker, that means that we're making more nitrogen dioxide gas. So it's already telling you which side this reaction is shifting to. It's shifting to the right-hand side. Sometimes there'll be a mark for that, but it's already telling you that, and you've got to explain why. Whenever you are answering a temperature question, you'll always start with whether the forward reaction is exothermic or endothermic. And they'll always give you a delta H value for the reaction. Here the delta H value is positive. It doesn't really matter what the value is, just whether it's positive or negative. The delta H value is always given for the forward reaction, so from left to right. So in this case, the forward reaction must be endothermic because it's a positive enthalpy change. So forward reaction is endothermic. And that'll get you the first mark. So you must always state what the forward reaction is. Then you say, therefore, reaction will shift. And you must use the word shift or move. You can't say goes or travels. You have to use the word shift or move. So shift to the right. And then you've got to say why, and that's in order to oppose. And then you just say what the change is to the condition. So you say to oppose the increase in temperature in this case. You can't just say just to oppose the change or to oppose the change in temperature. You have to be specific about what that change is. So first state whether the forward reaction is exothermic or endothermic, then say which way the reaction will shift and why it will shift that way. And you have to say to oppose whatever the change is. So in this case, to oppose the increase in temperature. This next question is asking you why the pressure might affect the equilibrium. So it says use Le Chatelier's principle to explain why the amount of NO2 decreases when the pressure is increased at constant temperature. So we're increasing the pressure, that means we're squeezing the reaction, so the reaction is going to shift to the side with less moles. But in order to answer this question, you've got to approach it in a structured way. So the first thing you do is you state how many moles of gas there are on both sides. So you say there are 2 moles of gas on the right-hand side, and you can use the abbreviation RHS if you want, and 1 mole of gas on the left-hand side. Then you say which way it shifts and why. So you'll say, therefore, reaction will shift, in this case it's to the left, in order to, either you can say to decrease the pressure again, or you could again use the same principle as last time to oppose the increase in pressure. So I'm just going to go through a few more of these sort of questions so you can see these principles being put into place. So first question says state what is meant by dynamic equilibrium. So the first point says there's 2 marks. First point, rate of forward reaction equals rate of backward reaction. And concentration of reactants and products do not change. So it's the same sort of question as stating 2 features of the dynamic equilibrium. And then it says state and explain how the total pressure in this equilibrium should be changed to give a high equilibrium yield of NO2. So we want to make more nitrogen dioxide. We want to say how we can change the pressure. So first look how many moles of gas are on both sides. There are 3 moles on this side and 2 moles on this side. So therefore we're going to shift to the side with fewer moles. So we're going to have to increase the pressure, squeeze it, so that it shifts to the side that takes up less space. So we're going to increase the pressure to increase the yield of NO2. And the reason, or the explanation, follows the same principles as before. So you'll say how many moles of gas are on each side. So there are 3 moles on the left and 2 moles on the right. And then you say, therefore, equilibrium will shift to the right in order to oppose the increase in pressure. Then it says, state and explain the effect of an increase in temperature on the yield of NO2 in this. So again, we're going to be looking at the delta H value. So if we increase the temperature, then it's going to shift the endothermic side, the side that cools down the reaction again. And you can see that the delta H value tells us that the forward reaction is actually exothermic because it's a negative enthalpy change. So the backward reaction must be endothermic. So if we increase the temperature, it's going to shift to the other direction, the backward direction. And so therefore the effect is going to decrease the yield of NO2. Again, the explanation, first say what the forward reaction is. So forward reaction is exothermic, and so therefore this is going to shift to the other side. So therefore equilibrium shifts to the left hand side in order to oppose the increase in temperature. Now in an exam, make sure you do not use these abbreviations that I've just used. I've just used those in order to fit all the words in. But you must make sure you use full words. The only things you can do is use this abbreviation here, LHS or RHS for left hand side or right hand side. Here's another question based on the same sort of thing. So this first question says, state and explain the effect of decreasing the temperature on the equilibrium of hydrogen iodide. So here we've got to look at the enthalpy change, which is -10. Remember, that's for the forward direction. So that is going to mean that the forward direction is exothermic. So if we decrease the temperature, it's going to shift to the exothermic side to heat back up again. And so it's going to shift to the right-hand side. So the effect on the yield of hydrogen iodide, which is the stuff on the right-hand side, is that it's going to increase. The explanation, remember to follow the rules for the temperature. So first state what the forward reaction is. So forward reaction is exothermic, and then you'll say that equilibrium, or the reaction, will shift to the right in order to oppose the decrease in temperature. The reason I've chosen this example is because this next question really, it says state and explain the effect of increasing the pressure on the equilibrium yield of hydrogen iodide. Now you'll see that this time there are 2 moles of gas on both sides, and so increasing or decreasing the pressure won't have any effect in this reaction because it won't favour either side. So you'll say that it have no effect, and you'll see there are only 2 marks for this question because the reaction doesn't shift, and all you have to put for the explanation is there are the same number of moles of gas on both sides. You can add to that, therefore the equilibrium will not favour either side if the pressure is changed if you like, but that's what will get you the mark. Then it says explain why an increase in the concentration of hydrogen gas increases the equilibrium yield of hydrogen iodide, and you can say here that the reaction shifts to the right hand side in order to use up the added hydrogen. And then it asks you to explain why the addition of a catalyst does not alter the position of equilibrium. And here you have to say that the catalyst speeds up the rate of a forward and backward reaction by the same amount. And that you get your 2 marks. The first mark is saying the catalyst speeds up the rate of the forward backward reaction, and then the second mark is saying that it's by the same amount each time. This last question I'm going to show you is kind of where the exam board seem to be going with these equilibrium questions recently, and it's kind of amalgamating 2 different topics. So it says when chlorine gas dissolves in cold water, a pale green solution is formed. In this solution, the following equilibrium is established. So there's the equilibrium. It says give the formula of the species responsible for the pale green colour in the solution of chlorine and water. Now the pale green colour is the chlorine. So that first mark is to say Cl2. Then it says use Chatellier's principle to explain why the green colour disappears when sodium hydroxide solution is added to this. So what you've got to notice is there are H+ ions in this reaction, and sodium hydroxide will react with those H+ ions because sodium hydroxide is an alkali and H+ ions are acidic. So you would say that the NaOH will react with the H+ ions. Therefore removing them. And then you would say therefore the equilibrium will shift to the right hand side in order to replace the lost H+. So in this case they're expecting you to realise the H+ will react with the sodium hydroxide. And that's basically reducing the concentration of the H+, and so the equilibrium will shift to make more of it. And so as it makes more of it, this Cl2 is used up, and so that green colour that the Cl2 produces disappears because it's being used to make more of all these products. I hope that's okay, and if you have any other questions, please make sure you email me with them.